Alright, welcome back to the FRQs from 2003's AP examination. Looks like we are going to tackle the three non-calculator FRQs, starting with this one, number 40. So it says, let f be a function defined on the closed interval from -3 to 4, with f of 0 being 3. The graph f prime, the derivative of f, consists of one line segment and a semicircle as shown above. So, again, first thing we're looking at is we are looking at a derivative graph. Now, this should be a pretty run-of-the-mill kind of question at this point. We can pretty much, without even looking at these questions, kind of guess as to what they're about to ask us, and, unimaginatively, they are going to ask us for part A. On what intervals, if any, is f increasing, and we have to justify our answer. Remember, please be careful with your English on this one. So it looks like in part A, we're going to have to just find out where the function is increasing. Well, where the function is increasing is where f prime is a positive value, right? So where f prime is positive, that is going to be where our f function is increasing. So we can pretty much assume that between -3 and -2, f is increasing. But the justification is going to be where we make or break our points. So we can start off by saying on the interval, I'll go ahead and move that. On the interval -3, -2, f is increasing because f prime is not increasing, right? F prime is positive there. And there you have it. That is part A. Pretty simple, pretty simple. So it looks like part B says find the x-coordinate of each point of inflection on the graph of f on the open interval -3 to 4. Justify your answer. Okay, so again, pretty simple in terms of what we're looking for. If we're looking for points of inflection, we're looking for where the slope of f prime is going to change direction. So I'm looking for the slope of this graph. Not this graph, but the slope of this graph. Well, it seems to change direction in two places. Right, whoa, you can't see that. Right here, and that's horrible. Right here, and right here. Okay, and so let's go ahead and justify that answer. So it seems like at x equals 0, move that, and at x equals 2, f has points of inflection because, now you can justify this in a couple of different ways. You can say f double prime changes signs there. Alternatively, you could say the slope of f prime changes direction or sign. Go ahead and move direction down. There. Either one of those will be fine. Okay, cool. Let's see here. Write the equation for the tangent line to the graph of f at the point 0, 3. So in order to write the equation of a tangent line, I need a couple of things. I need a coordinate set, and I need a slope. So it's a good thing what we're being asked to do is to find the equation of the tangent line at 0, 3. Notice how they give you the information at 0, 3 right there. So we can start this off by saying y minus 3 is equal to some kind of x minus 0. And what we need to do now is we need to find out the slope right there. Well, what is the slope? Well, the slope is going to be the value of this coordinate right here. So the slope at 0, in other words, f prime at 0 is -2. So that is what goes into there, and you're done. So again, pretty straightforward FRQ. Hopefully this isn't giving you too much of a problem. So in part D, we're being asked to find f of -3 and f of 4. Well, how do we do that? We know that f of -3 is going to call upon some information. Well, I know that as long as I use this information that's up here given to me, the f of 0 being 3, and I use this coordinate to find what I'm looking for, then I'll be all good. So I'm going to use a little bit of integration. I'm going to integrate from negative 3 to 0 of f prime of t dt. And realistically, what that gives to me is it gives to me f of 0 minus f of negative 3. Remember, f of negative 3 is what I'm solving for, so I'm going to get that by itself. I'm going to go ahead and add that to this side, and I'm going to go ahead and subtract my integral from the other side. So what does that give me? It gives me f of negative 3 equaling f of 0 minus the integral from negative 3 to 0 f prime of t dt. Well, we know that f of 0 is 3. They gave us that right up here. Well, what's the integral from negative 3 to 0 of f prime? Well, that's just the area under the curve of this line right here. So what do I get? I'm going to be subtracting. I have a triangle and a triangle. I have this triangle up here, and I'm going to be adding it to this triangle that's below. And since I'm subtracting the sum of two triangles, I'm going to go ahead and just subtract the entire thing, just to keep myself safe. Let's go ahead and get the dimensions of the triangle. This triangle here is 1 and 1. This triangle here is 2, and because I'm adding these values together, this 2 is going to become negative, because it's technically negative area. So what I've got here is 3 minus, well, what I've got is base times height times 1/2 is going to give me 1/2 here. Base times height times 1/2 is going to give me minus 2 here on the right triangle. So what does that become? Well, I have 3 minus, what's 1/2 minus 2? Well, that's negative 1.5. Whoops, 1.5, not negative 1/2, negative 1.5. 3 minus negative 1/2 is this, negative 1.5 is going to be the same thing as adding, so what I get is 4.5 as my final answer. And there you have the first part of part D. If you need to, go ahead and pause and get this copied down or watch it over again. I'm going to pause for a second and clean up some of this so I can do the second part of part D. I'll be back in a flash. The second part of part D asks us to find f of 4. So it's going to be done the exact same way. I'm still going to integrate from 0 to 4 of f prime of t dt. Well, what does that give me? It gives me f of 4 minus f of 0. Easier than the first part, I'm actually going to just add f of 0 to both sides. So I'm going to kick that over. So I know that f of 4 is equal to f of 0 plus the integral from 0 to 4 of f prime of t dt. Well, still, f of 0 hasn't changed. That's still 3. And now I'm going to add that to my area between 0 and 4. Now, hang on for a second. Here's where it gets a little messy. The area is technically this portion right here. I'm going to color it in green. This is what they want right here. But we've never really had to get that type of area before, so it's a little odd. How do we do this? Well, it's almost like old problems in geometry when we had to find the area of the shaded region. So what I'm going to do is I'm actually going to go ahead and find the area of this rectangle right here. So let me draw this in black. I'm going to find the area of this rectangle here first. And once I do that, I think some of you guys are going to kind of see where this is going. So the area of the rectangle, so I'm going to add that here. The area of the rectangle is simply base times height. And then what I'm going to do is I'm going to go and subtract the semicircle from that rectangle, and that'll give me my green area. Hopefully that makes sense. Let's see here. The rectangle has a base of 4, and it has a height of negative 2. And then the semicircle has a radius of, looks like, 2. So, how does this turn out? Well, what I've got here is I've got 3 plus negative 8. Now I'm going to be, remember, this area here is going to be subtracting this area. But because this half circle is also negative, I'm really subtracting negative area as well. So a half circle is going to be pi r squared. So the r is 2, so pi r squared divided by 2. So what does this turn out to be? It turns out to be 3 plus negative 8. Negative negative is positive. I get a 4 pi over 2, so it looks like it's going to become a 2 pi. And ultimately what I get is, after combining these guys, I get negative 5 plus 2 pi. And that is f of 4. Alright, there you have it. That is the first non-calculator FRQ. Let me go and clean up this board real quick, and I will be back for the second one. See you in a few minutes. And we're back. Yes, apparently a few minutes does go pretty fast sometimes. So, looks like we're dealing with the second FRQ here. A coffee pot has the shape of a cylinder with a radius of 5 inches, as shown in the figure above. Let h be the depth of coffee in the pot measured in inches, where h is a function of time, t, measured in seconds. The volume v of coffee is changing at a rate of negative 5 pi rad h cubic inches per second, and the volume of a cylinder is v equals pi r squared h. Okay, cool. So what do we know about this problem so far? We know that dv over dt, the change in volume over time, they gave that to us. That's negative 5 pi rad h. Okay? And then they also give us that r is 5. Now, how does this play a role here? Just like the rain collection problem, and unlike the ship that had the tanker explode problem, this radius is going to be constant, because, you know, in the real life, you got to just kind of think a coffee pot is not going to be changing shape as we fill it with coffee. It's a can, it's a coffee pot, it's definitely going to be consistent. So really, when we look at the volume of this, it's really not just pi r squared h, it's really pi, something simpler than that. It's pi times 5 squared h. And again, we can deduce this because it's a coffee pot. In the real world, coffee pots don't expand when it comes to them getting filled with coffee. It's not made of rubber, it's probably made out of metal or something like that. So we really know that our volume is 25 pi h, which makes our derivative a lot cleaner, because now we can avoid product rule altogether if and when we go to derive this function. So anyway, I think that's what they're going to ask us to do in the first problem here. We need to show that dh dt is equal to negative rad h over 5. So we know that dv dt is going to equal, if I use this as my v formula, it's going to be 25 pi dh dt. So how do we solve for dh dt? Well, we know a couple things. We know that dv dt is equal to negative 5 pi rad h. And we know that that equals 25 pi dh dt. At this point, it really becomes an Algebra 1 problem. I'm going to go and cancel the pi's, because we can. If I divide both sides by 25, what I get is dh dt equaling 5 over 25 is going to be negative 1/5. So technically negative rad h over 5. We have proved it. We are good. And life goes on. Okay, next piece. Given that h is equal to 17 at time equals 0, solve the differential equation for h as a function of t. Okay, so it's a differential equations problem, diffq. So knowing that h equals 17 at time equals 0, that's actually giving us our initial condition, 0, 17. We use this in order to solve for c, our constant, right, that pops out whenever we integrate. So let's go ahead and do some differential equations here. We've got dh dt is equal to negative rad h over 5. And so first thing in a diffeq, please remember, separate your terms out. Okay, so how do we do that? Well, I'm going to go and get the dt over to this side, and I'm going to get the 1 over negative rad h on this side. Actually, I think I'm going to keep, I changed my mind. I'm going to keep 5 negative. I feel like it. Keep this thing negative. All right, so now what I've got here is I've got 1 over rad h dh is equal to negative 1/5 dt. So again, we've separated our terms. We're all good. Now I can go ahead and integrate both sides. And what I get here is I'm going to end up getting, this is really h to the negative 1/2. So what I get on the left side is going to be h to the 1/2 times 2, because of my reverse chain ruling. Clean up that 2 a little bit. And that's going to equal negative 1/5 t plus c. So I think at this point, I'm actually in a pretty good position to solve for c. Knowing that my initial condition is 0, 17, I can go ahead and solve for c pretty easily. So what I get here is I get 2, h is 17, so 17 to the 1/2 is rad 17 is equal to negative 1/5 times 0 plus c. Well, luckily that just goes away. And I end up with c equaling 2 rad 17. I'm going to save that because I'm going to end up going back to this function here and punching it in and then getting h by itself. So what I get is I'm going to go ahead and keep writing this as a square root for now. I can go ahead and divide out the 2 from everything. So what I get is rad h is equal to 1/2 times negative 1/5 t plus 2 rad 17. If I distribute that in, remember I'm dividing out the 2, I'm getting rad h by itself, I get negative 1/10 t plus rad 17. The 2's are going to knock each other out because one's on top and one's on bottom. And that equals rad h. From here to get h by itself, I'm going to go ahead and square both sides. So what I get ultimately is h equaling negative 1/10 t plus rad 17 quantity squared. And that is my function of h as a function of t. Okay? Now, the last part of the question here is saying, at what time t is the coffee pot empty? Well, how do we find out? There are a couple of ways we can find out when the coffee pot's empty. One, if the volume is 0, that would be true. There would be no coffee in the coffee pot. But another way we can do this, because we don't have a formula for volume right now as a function of time. All we have is a function of height as a function of time. But hopefully it should make sense that when the height of the coffee pot is nothing, then the coffee pot is empty. So as long as I let h become 0 and solve for t, I can figure out when this coffee pot is empty. Okay? So square root both sides. That kills off that. And so what I get is 0 equaling negative 1/10 t plus rad 17. Do some algebra, kick the 17 over, or you can even kick the 1/10 t over, equaling rad 17. So t equals 10 rad 17 by multiplying both sides by 10. That is when your coffee pot is empty. Okay, cool. Let me go ahead and clean up the board, and I will see you again very shortly. And let's get ready to go ahead and take on the last FRQ from our Non Calculator 2003 AP examination. So, let's see. Let f be the function defined by that piecewise deal. You guys can go ahead and read that. Part A, is f continuous at x equals 3? Explain why or why not. Okay. Well, to justify our answer will be pretty easy. We just have to show that the limit from both sides is going to equal, and that f of that value is going to equal. Okay, so how do we justify this? Part A. Well, if we look at the limit as x goes to, looks like the point in question is at 3, so to 3 from the left, looks like we're going to call upon this function here, this rad x plus 1. Now, we also know that because of this little equal sign, that also equals f of 3. So if I find the value of 1, I found the value for both. And then, let's see, if I take the limit as x goes to 3 from the right side, well, that's going to be this 5 minus x function. So the numbers that I get out of these two equations, or these two limits, should be equal if the function is going to be continuous. Well, let's see what we get. If I plug in a 3, it looks like I'm not in trouble, so I take the square root of 3 plus 1, which is 4. Just kidding. So if I take the limit as x goes to 3 from the left, of this function, what am I going to get? Looks like I'm going to get a 3 plus 1, which is 4. Square root of 4 is going to be 2. And then what we've got here is 5 minus 3, which is still going to give me 2. So what can I conclude? I can conclude that yes, by the definition of continuity, the limits agree from both sides, and f is defined in the place where the limits agree. Therefore, f is continuous at x equals 3. Long story long, you don't need to get that far into detail of it. The work is enough justification. You could just say yes, by the definition of continuity, f is continuous at x equals 3. But I'm just really hammering that point home for them. Okay, cool. So find the average value. Okay, so we all know what question I like to ask when we hear the words average value, so I won't even ask it. But we have to find the average value on the closed interval from 0 to 5. So it looks like I'm going to be multiplying both of my integrals, and I say both of my integrals because I'm going to have two. Looks like I'm going to multiply both of them by a 1/5 because it's the average value on the entire interval. So I'm going to go 1/5 integral. Looks like I can only integrate from 0 to 3 for the first piece. So that's going to be x plus 1 to the 1/2 dx. And then I'm going to add that to another 1/5 integral from 3 to 5. And that's going to call upon my 5 minus x dx. Okay? So at this point, it's just a matter of simple integration. So it looks like this thing here is going to integrate into, looks like an x plus 1. 1/2 plus 1 is going to be 3/2, but this thing needs a 2/3 on the outside in order to unchain out, or in order to cancel out the power rule. And don't forget, this is being multiplied by a 1/5. Okay? And that's also on the interval from 0 to 3. I'm going to go and leave the right side alone. I think some of you guys are going to know what I'm going to do. It's a 5 minus x function. Should be relatively simple to do without taking a proper integral of this thing. So let's go ahead and just handle this side here. So I'm going to go and leave the 1/5 out just because I feel like it for now. And I'll leave the 2/3 out. So in fact, I can go and multiply those together to make them 2 over 15. And then I'm going to go ahead and evaluate this expression at 3 and 0. So it looks like I'm going to get a 4 if I punch in a 3, and then I get 4 to the 3/2 minus. Now you want to be careful here. This 0 can be a little bit misleading. 0 actually does give you a value right here, so make sure you guys are not saying, oh, it's 0, I don't have to include it. People can get really messed up by that. So 0 is going to give you a value. It's actually going to give you 1. So make sure we're being extra careful about that. So what I've got here is 4 to the 3/2. Well, that's going to give me 2. 2 to the third is 8. So what I have is 8 minus 1, which is 7. 7 times 2 over 15 is 14 over 15. Now, I've left this part alone up until now because I think some of you guys are going to be able to figure out what I'm about to do. What I've got here is I'm actually going to go ahead and use geometric integration. Now, you can go ahead and use standard integration if you want to. It really is just a matter of taste and style at this point. So here's what I'm going to do. I have a right triangle here. Remember, I'm only integrating from 3 to 5, so I got to be careful. I'm not going from 0 to 5. I'm going from 3 to 5. So from 3 to 5, my base is 2. If I plug in a 3, my height is also 2. So what I've got is 1/2 base times height. So those are going to knock out. I end up with just a 2, but don't forget it's multiplied by 1/5. So that is what I have. Now from here, I'm going to need a common denominator. So what I've got is I've got 14 over 15 plus, looks like if I multiply the top and bottom by 3, then I'm all good. So what I've got here is 6 over 15, which is 20 over 15. Okay, let me pause for a little bit so I can clean up the board, and then we will tackle part C. Part C is we're supposed to have another piecewise function that's g of x, and we're supposed to find out the values of k and m if g is differentiable at x equals 3. So the fact that g is differentiable at x equals 3 implies that the function is continuous at x equals 3. And so what we've got to do is we've got to use that information to solve for k and m. We've done many problems like this, reviewing for midterms and finals and all the rest. So let's just go ahead and get to it. If the function is continuous at x equals 3, what that means is that the limit as x goes to 3 exists. And here's what that tells me. It tells me that I can go ahead and set 3 inside for x for both of these. What I can do is I can say that k rad 3 plus 1 is going to equal 3x plus 2. Okay, the fact that the limit exists means that they agree from both sides, which means this limit will equal this limit at x equals 3. Okay? Again, you don't need to write that part down. I'm just kind of explaining. Okay, so, oops, didn't want to get rid of that. So let's go ahead and solve for these. This becomes a 4, this becomes a 2, so I've got 2k equaling 3x, oh, not 3x, sorry, what am I saying? 3m plus 2. That is not supposed to be an x, that is supposed to be an m. 3m. Well, here's the problem, is that right now I've got two variables, and I need a second equation. Well, the fact that g is differentiable helps out immensely. So what does this derive into? Well, the top function will definitely derive out. What I've got is g prime of x equaling, if this is k times x plus 1 to the 1/2, I've got 1/2 k times x plus 1 to the negative 1/2 up top. And then on bottom, it's linear. So what I've got is I've just got m. And these are under the conditions that x is in between 0 and 3. And this is for when x is between 3 and 5. Again, the point in question is 3, so the 3 was really the only thing that I cared about. So let's go ahead and plug 3 in for each of these. So if I plug a 3 into here, what I have is 1/2 k over the square root of 3 plus 1, and that's going to equal m. Now, why am I able to set these guys equal to each other? Because the fact that the function is differentiable means that its derivative, for the most part, is going to be continuous. Again, there are those exceptions every once in a while, but this is not one of them. So here's what I've got. I've got a 2, 4, so k over 4 equals m. So in other words, m equals 1/4 k. Well, how do I use that information? I can use that information to punch into here. So what I've got is 2k equaling 3k over 4 plus 2. Let's go and get a common denominator here. This is really 8k over 4 equals 3k over 4 plus 2. Subtract, I've got 5k over 4 equals 2. 8 divided by 5. K equals 8 over 5. Again, I multiplied the 4 and then I divided by the 5. Okay, so how does this help me? I can go and punch this information back into this guy. So what I've got is, I'm going to go and separate this out a little bit. I've got 1/4 times 8 over 5 equals m. Goodbye to you, a 2 up top, 2/5 equals m. And there you have it. Overall, I think 2003 was a pretty good year to be an AP student. But hopefully you guys found these FRQs relatively straightforward. Yeah, we will see you later.